Welcome. I'm Casper Moltzer from the Radboud University, and today I'll be presenting my first project, understanding post-RGB binaries through stable mass transfer, with regard to my PhD project investigating the evolution of post-AGB binaries. I do this work supervised by Onno Bols and the previous speaker, Hans van Winkel. And with this project, I've also had help from Karel Temmink and Maarten Weideveld. So let's start with what is a post-AGB and / post-RGB binary. Hans already touched upon it. And what they are a binary containing a post-AGB or post-RGB star with what we think is a main sequence companion. And as Hans already said, these are most likely surrounded by circumbinary disks. And we even see jets emanating from these systems. This is all shown, all these components in this schematic on the slide. And what I'm showing here is our Galactic post-AGB binary sample plotted in the HR diagram. And the dashed line here denotes the RGB-tip luminosity. And it is thought that the objects above this line are post-AGBs, and the objects below this line are post-RGBs. And that is the case because an AGB star would have been too luminous to create such objects, and thus they must have come from the RGB, and thus they're called post-RGB stars. What you can also see is the color bar, which shows the orbital periods of these objects. And let's investigate these orbital properties just a bit further. Here I'm plotting them, so period on the x-axis versus eccentricity on the y-axis for our galactic sample. And you can see that there are circular systems, but there are also pretty highly eccentric systems all the way up to 0.63. And the periods range from around 50 to around 2000 days. And this is actually kind of problematic. Hans already kind of showed it. So here I'm showing once again period versus eccentricity. And red data markers are once again our post-AGB sample. And the blue here shows what binary population synthesis predicts. And what you can see is that it predicts an bimodal orbital period distribution. And the orbital periods of our objects precisely fall within this so-called period gap. And this is not the only type of binary that has this problem. There are other post-interaction binaries that have that fall within this period gap, like barium stars and white SDB stars, for example. And just touching a bit on this bimodal orbital period distribution, if the binary is initially wide enough, then they won't really interact, meaning that the giant star will just lose its envelope via wind mass loss, and that will widen the orbit. So that's this movement to the right in the diagram to higher periods. But if the companion is close enough, then a binary interaction will occur. And here I'm showing a schematic of how that looks. So the primary swells up and starts filling its Roche lobe, which is denoted by this figure of 8. And then mass will start transferring from the setup point onto the companion. And for giant stars, like AGBs and RGBs, it is thought that this process is unstable. So it's a runaway process, meaning that the star will start expanding more and more when it's transferring the mass, and it will kind of engulf this companion. And when that happens, the orbit is made more narrow. So that's this movement to the left, and this is called a common envelope. And before this binary interaction can really occur, the companion is close enough to this swollen star that tidal interactions will occur and which will circularize the orbits. And that is why for this parameter space, you also really wouldn't expect eccentric orbits to occur, which is also not really the case in a lot of these samples. But what I'm interested in is a stable mass transfer. And what that means is that it's another runaway process and the star will nicely keep filling its Roche slope just about, and a companion with can deal with the mass being put onto it. And this is important because the paradigm that RGB donors are always unstable with regard to mass transfer is actually outdated. My collaborator Karel Temming and others in 2023 showed that mass transfer from RGB donors is stable for many binary configurations, and this is precisely what I'm going to probe with this research. So what I do is a lot of binary modeling using the stellar evolution code MESA, and I probe the parameter space of initial primary masses of 1 to 8 solar masses, so really the low and intermediate mass regime. And I do this for initial binary separations from the post-main sequence to the start of the TP-AGB. On the right panel are the evolutionary tracks of the donor stars that I use, and the white markers show at what time I start these binary interactions. And I do this for mass ratios of 0.1 up to 1 solar masses. And this is done for 2 different metallicities, a supersolar grid of around 140% solar metallicity, and a metal pore grid of around 10% solar metallicity. And the following 2 assumptions are made. Firstly, that the mass transfer is conservative. And this might seem weird because we see these circumbinary disks, right? However, we don't really fully understand how non-conservative this mass transfer should have been. So for simplicity's sake, for the modeling, we assume conservative mass transfer. And this is also the case for eccentricity. So we assume circular orbits. Furthermore, from these models, we make the selection that the mass transfer has thus need to have been stable, that the system is post mass transfer, that the effective temperature falls within the interval of our sample, so 4 to 8,500 Kelvin, and that the luminosity is dominated by the flux of the primary, because in our observations, we do not see the secondary really. So with this all taken into account, here are my models. So what I'm plotting is luminosity versus orbital period. And this is done because those are kind of the 2 main observables from our observed sample. So this goes a long way with being able to compare with the observations further down the line. On the left, you see the supersolar grid, and on the right, you see the metal pore grid. And what I first want to pull your attention to are the post-RGBs denoted by the circular markers. And what you can see is that they follow a really tight luminosity-orbital period relation, which is very useful because it gives us a lot of predictive power. What you can see is that these all have progenitors of initial mass 1 to 2, but not including 2 solar masses, so really the low mass stars. And because of the IMF, these are going to be most abundant. So this luminosity regime should really be dominated by these post-RGB stars following this tight luminosity-orbital period relation. And just comparing the 2 relations with regard to metallicity, here I've just plotted very simple polynomial fits of the 2 to highlight it a bit better. You see the supersolar grid in blue and the metal pore grid in red, and you can see that the metal pore grid is slightly shifted downwards for orbital period. And this is the case because metal pore stars are more compact in nature. So for the same luminosity, you will have a smaller star and thus will need to be in a shorter orbital period to undergo binary interaction. So that's what's going on there. Then I want to draw your attention to this other set of post-RGB stars. They have progenitor masses of 2 to 2.5 solar masses. And you can see that these do not follow this strict luminosity orbital period relation. And this is the case because around this parameter space, the core of an RGB star starts becoming non-degenerate, which means it will not follow tight core mass luminosity and core mass radius relations, meaning it starts deviating from our luminosity orbital period relation. However, this is a pretty confined and specific parameter space, it is thought at least, and thus we think that these won't be very abundant within our sample, and thus they will not be investigated further with regard to comparing it to the observations. This is also the case for the next class of objects, which are denoted here by the crosses, so the pre-subdwarfs. So what's going on here is that the post-RGB star, during the mass transfer, its core has just become massive enough for helium ignition to occur. So we'll start moving to the extreme horizontal branch. So we'll start contracting, heating up, but also lowering in luminosity. And that's why you can see this movement to the left of the diagram. So still high orbital period with regard to the post-RGBs, but moving to lower luminosities. But once again, this is a pretty confined parameter space, so we won't be taking those into account further with regard to analyzing our sample. Then you have the post-AGBs shown by the squares. Firstly, you see some overlap in the high luminosity regime of the post-RGBs, but you can see that the progenitor masses are 2 up to 8 solar masses. So these are going to be less abundant through the IMF, and also this is a quicker evolutionary phase than post-RGB. So we once again think that post-RGB should dominate within this regime. Secondly, we did not include the TP-AGB in our grid of models, so it's very difficult to analyze this parameter space, so we won't be doing that with regard to our sample. But I want to draw your attention to that you see a lot of spread luminosity and orbital period wise with regard to the post-RGBs. So it shows that future research into understanding these post-AGBs is going to be much more complicated than for post-RGBs. And then lastly, you have this final object type, these central helium burning stars. And what these are objects that underwent mass transfer during the Hertzsprung gap, so just before this star reaches the RGB, and this star expands way slower in the Hertzsprung gap than on the RGB, so the mass transfer will take place on a much longer time scale, thus most likely being much more conservative, meaning that the companion can grow more and become a lot more luminous. So the object should actually be moved most likely more to the right, and most likely you would also see the companions then. And this is not the case for our observed sample, and these also have very high progenitor masses, so we also don't take these into consideration further when comparing it to our observed sample. But before we can compare these models to our observations, we need to take into consideration once again that a good few of them are eccentric, and then you need to kind of interpret the orbital period slightly differently, because then mass transfer must have occurred at periastron, which is the closest distance between the companion and the donor, which is shown in the figure here. And the periastron distance is related to the semi-major axis with a factor of 1 minus e eccentricity. And through Kepler's third law, this is then related to the orbital period. So to be able to compare these eccentric binaries to our circular models, we need to correct the orbital periods with a factor of 1 minus e to the power of 3 divided by 2, which explains the y-axis here. So what I'm doing is exactly that, comparing our luminosity orbital period relations to our observed sample. And what you firstly see is that there are not any low luminosity or low orbital period objects in our sample. But this is because due to a selection bias by how historically the sample has kind of been cobbled together. Then you see a lot of objects in this high luminosity post-AGB regime, but like I said, we do not include the TP-AGB in our grid of models, so we won't be investigating this space any further. So let us zoom in what we're interested in. And you see that there are 2 different types of data markers. You have the stars, which are the spectroscopic orbits. So here, the orbits have been found via radial velocity monitoring. But you also have this other method shown by the diamond, and this is photometrically, so variability in the light curves. And the disadvantage of this method is that it doesn't give the eccentricity of the orbits. So the dashed lines downwards show how much the orbital periods could be translated downwards to a maximum of the observed eccentricity within our sample, so 0.63. So it's kind of a theoretical error bar. And this is compared to the theoretical, solid error bars, which are the observational uncertainties. So what you see here is that that a lot of the observed systems do seem to line up with our observed luminosity orbital period relation. You do have this one object above here, which is pretty high above the relation, but this is only determined photometrically. This is BT lac, and for it to coincide with the relation, it would roughly need to have an eccentricity of 0.43, which is not out of the ordinary. There are a lot of objects with that eccentricity within this subsample. So I think all in all, the take-home message is that galactic post-RGB binaries seem to follow stable mass transfer. However, there is a caveat, and the caveat is that after mass transfer, some of the post-RGB binaries are still eccentric, which is not in line with orbital circularization by tidal forces. So all in all, the orbital period problem seems to be fixed, but there's still an eccentricity mystery. But that's a story for a different time. So I look forward to any questions from the audience, and thank you very much for listening to my talk.
Thank you very much.
There are still some post-RGB, post-common envelope objects where clearly there has been unstable mass transfer. So is there a mass bias or any other kind of bias to segregate out the population that go into common envelope to those that don't go into common envelope?
Yes. So I personally find that there's a lot of discussion recently about the common envelope nature of these objects. Actually, if you, for example, also look at ELCVN binaries, which seems to kind of be the really low mass comparison to these post-RGB stars, they also seem to kind of follow a stable mass transfer. So I personally find it pretty difficult to say about these objects which might seem connected to common envelope evolution. And I think this also kind of needs to be investigated more properly with these understandings that we now have of a stable mass transfer. So all in all, I have to say it's kind of difficult to answer that question.
I do have one. So you find this very nice, very tight luminosity-orbital period relation? Yeah?
Yes.
So my question is, isn't that like a natural consequence of the assumption of conservative mass transfer? Have you tried, tested? Because I can imagine that if you lose some angular momentum and mass, that should change. So have you tried how sensitive this relation is to the assumption?
So it's stable mass transfer is not an assumption here. It's a selection.
I said conservative mass transfer.
Conservative mass transfer. Yes, that's a very good question. If I could just very quickly show my backup slide, that's one of the things that is listed on my future to-do list, looking into this non-conservativeness of the mass transfer. Most likely there should be some slight deviation from the relation then, specifically for the orbital period, so y-axis wise, but it's pretty difficult to say how large this effect is going to be. So this is something I will look into further in the future.
Okay, I look forward to it. Thanks.